Today we look at the adiabatic reversible work. Adiabatic reversible work. Now, when we talk of adiabatic work, remember, as you had said in the earlier lectures, that means there is no heat transferred into the system. It's very important to always note that. And so, if you have to look at reversible work, then we have to fall back on the first law of thermodynamics, which tells us that du is equals to dq plus dw. And so, if we are dealing with adiabatic work, then that quantity vanishes straight away, it's zero. And if we are assuming that the gas is ideal, which is what we are assuming here, if we assume that the gas is an ideal gas, assume the gas is ideal. In other words, it obeys the ideal gas equation of state PV is equals to nRT. Then, based on our earlier experiments and discussions using Joule's experiment, we saw that du is equals to Cv dt, because that coefficient which was being determined using Joule's experiment, which was del u del v, t constant, was 0. Therefore, in place of du, we can replace that with Cv dt, so that Cv dt is equals to dw. And dw for PV work, we had already said in our earlier lectures when we derived the first law of thermodynamics, and then we looked at the reversible and irreversible work. We saw that dw for PV work is always minus P dV. Now, if it is minus P dV, again, you can put in the expression for pressure based on the ideal gas equation of state. Ideal gas equation of state is not the only equation of state. There are other equations of state. The Redley-Kwong equation of state, we have the Beatty-Bridgman equation of state, the Bartolotti equation of state, the Varial equation of state. There are many equations of state, but we choose the ideal gas one. So that we have Cv dt is equals to minus nRT over V dV. So if we rearrange this expression so that we put the like terms together, then we'll have Cv over nR dt over t is equals to minus nR dV over v. So I've divided by t, and so we end up with the expression which you have there. Now, I don't want to keep carrying this bulky expression Cv over nR. Let me call it C. Let's call it C. Let's call it C, so that our lives are a bit easy. Now, if we integrate that particular expression there, then we'll have C integral of dt over t is equals to minus nR dv over v integral from some point, let us call that some initial value, some final value, initial value, some final value. Remember, those initial values represent the initial state, and the final value represents the final state. Using the integral calculus identity, that dx, like we had mentioned when we were deriving reversible work and reversible work, this identity dx is simply natural log of x plus c. Remember, natural log is log raised to base e, log to base e, that is e is 2.718, is not the normal log to base 10. So we have that expression there which we can apply to our earlier equation, so that we have c natural log of t final over t initial is being equal to minus nR natural log of v final over v initial. Again, I'll use logarithmic identity. That is, if you have minus natural log of m over n, I can remove the negative sign by inverting the coefficients. I have n over m. So I'll apply that to the term on the right. So we have Cv, C in TF over Ti is equals to plus now NR in V initial over V final. So we just use the logarithmic identity there, which is very, very simple. And so we need to define some new term which we call gamma. We need to define a new term which we call gamma. And that gamma is the ratio of the heat capacities CV over Cp. That's the ratio of the isobaric and isochoric heat capacities. Don't confuse with gamma. There is gamma also in spectral lines, but normally gamma in most cases is Cp over Cv. So we'll say that 1 over C is equals to gamma minus 1. The C we are talking about here is our C, which was Cv over Nr, which we said was bulky, and we didn't want to carry it around. And just to convince ourselves that that is true, it represents what we're saying, we can say 1 over C is equals to gamma, that's Cp, over Cv minus 1. So if we take the LCM, then we have our Cv and Cp minus Cv. And what is Cp minus Cv? For ideal gases, Cp minus Cv is equals to Nr. That's true for ideal gases. Ideal gas. And so this expression is Nr over Cv, which is C is equals to Cv over Nr, like we had carried it out, like we had written or assumed, so that we don't keep carrying the Cv over Nr around. So we are in good shape in terms of that. So if we apply this particular quantity to our natural log of Tf over Ti, C, that becomes, we say that was natural log, that was Nr, natural log of, that was natural log of Vf, Vi over Vf. We had inverted it already, Vi over Vf. Again, we want to use the other identity, mathematical identity, which says that M natural log of L over P can be written as natural log of L over P raised to the power M. That's another important identity which you need to remember. So we can apply that on the expression on the left-hand side. So we have natural log of Tf over Ti raised to power C is equals to natural log of Vi over Vf. And so remember, when we have the two logarithmic quantities, natural log of M over N is equals to natural log of Y over X, then it implies that the quotients are equal. It implies that M over N is equals to Y over X. And so it means that Tf over Ti raised to power C is equals to Vi over Vf. So we can use that relationship there. So we say that Tf over Ti raised to power C is equals to Vi over Vf, Vi over Vf. And again, we use the identity of the exponents, so that if we say we have M over N raised to the power K is equals to Y over Z, we can change the exponents in the manner that is, remember this Y over Z is just like raised to power 1. And this is M over N raised to power K. So if I divide by K this side, I will have divided 1 by K. So we will have M over N is equals to Y over Z, the power 1 over K. So this exponent identity is what I want to use now to transfer the C to that side, so that I get it in the form 1 over C, because remember we said 1 over C is gamma minus 1. So we'll have Tf over Ti is equals to Vi over Vf raised to power 1 over C. We now can express as Vi over Vf raised to the power gamma minus 1, which is gamma again, remember we said was the ratio of the heat capacities. So once we have that expression, since we had assumed we are dealing with an ideal gas, we can use the ideal gas expression, that is Pf over Vf, Vf over Tf is equals to Pi VI over TI. That again is gotten from the ideal gas equation. PV is equals to nRT. So if you divide both sides, we say PV is equals to nRT. So if you divide both sides, if one P1, one T1, so you'll have that as P2, V2, and then divide, assume the number most the same. T2, of course, they'll cancel. If you rearrange them, then you get that particular expression we have there. Now we have this expression here, which you want to work with. So let us rearrange our equation here so that we have TF over TI from this expression for pressure, volume, and temperature for ideal gas. So if we do that, we just cross multiply the quantities. So we'll have, if we transfer TF to that side, we cross multiply, we'll have PF VF over PI. VI is equals to TF over TI. But what is TF over TI in terms of gamma? You have seen it is VI over VF. VI over VF. This is the power gamma minus 1. Again, we want to use the exponent identity so that if we have m raised to power n times m raised to power x, y, that quantity is simply m n plus y. We add the exponents. Of course, if you divide, then you have subtracted. So let us reorganize like terms together and use that exponent identity. So we will have PF VF gamma minus 1 is equals to PI VI gamma minus 1. And that's why I now use the exponent identity. That is, this becomes VF. Remember, that's raised to power 1 times VF gamma minus 1. So it becomes VF 1 plus gamma minus 1. And of course, those cancel. So you'll have VF gamma. So we have used that exponent identity there to simplify our expressions there. So let's now just apply it across the board and get expression there. So we have now, therefore, we will have now PF VF gamma is equals to PI VI gamma. Or we normally write this simply as PV gamma is equals to a constant, and this is true for ideal gases. Very important for us to note that. Now, this is a work expression. Remember, we said in our earlier lectures that PV is work, because if pressure, remember, is force over area, and remember volume is area times some length, so that the area comes with that force times length is simply work. So that's an expression for work. And so what is the indicator diagram for this adiabatic reversible process? That adiabatic reversible process. The indicator diagram, just like we saw with the irreversible and reversible works and isothermal conditions, we see that in this particular case, the pressure volume profile will be such that the slope for the adiabat, which we say is P directly proportional to 1 over V raised to power gamma, this is the adiabat, is much steeper than that for the isotherm. It's much steeper than that for the isotherm. That is P is proportional to V. And makes sense. When you're talking about an adiabat, you're not allowing heat into or out of the system. But when you're talking about an isotherm, you're allowing heat into the system. So you keep balancing. As you do work, more heat comes in, and the process continues. So that explains the difference between these two particular quantities. And so we will stop at that particular point and pick up the next lectures where we're going to deal with other thermodynamic quantities.